Welcome to a new lesson of heat transfer. Today we continue our discussion of radiation and heat transfer. We're interested in particular in the exchange thermal energy by radiation between two surfaces. This exchange thermal energy depends on the temperature of the surface, on the surface property, but also on the relative orientation of these two surfaces. Let's look at this sketch here. We have surface 1 and surface 2, and we have another surface here. So the heat transfer emitted by this surface from this point has the same intensity, but obviously more heat reaches surface 1 than surface 2 because surface 1 is in a different position with respect to surface 2. So surface 1 receives more heat from this surface than surface 2. So the question is, how can we account for this different orientation? So to do so, we introduce a geometrical quantity that's called the view factor. And the view factor is denoted by the capital letter F with two subscript I and J, where I indicates the surface I and J indicates the surface J. So the view factor Fij is the fraction of radiation leaving surface I that strikes surface J directly. So in this definition of purely geometrical quantity, the view factor, absorption and reflection are not included. So if you read the books, for example, the Cantor book on heat transfer, then there's a complete mathematical derivation of a view factor. So for example, F12, so view factor from surface 1 to surface 2, has this mathematical relationship. So A1 is indicated here, A2, and then we have to define an angle θ1, and θ1 is the angle between the unit vector that defines the surface, so perpendicular to surface 1, and the direction from the point that we're interested in surface 1 to the point that we are interested in on surface 2. And analogous is the definition of θ2. That's the angle between the unit vector n2 and the direction between the two surfaces. So F12 has a double integral over the two surfaces, and where the angle θ1 and θ2 vary. We're not going to integrate such a complicated expression. Instead, we can use graphical representations of the view factor. So, luckily for us, a lot of people have spent a lot of energy and effort to find plots. So to integrate those double integrals and to obtain graphs that we can use so we can easily find F12 for a particular geometry. We can just obtain it graphically. So a typical graph for view factors is in this form. So on the x-axis we have, for example, in this case, the length L2 of one of the rectangles indicated here, L2, and D is the distance between these two plates. So we know the value on the x-axis, and we move up and we stop on the pink line of interest. The pink line refers to one of the ratio between L1, that's the other dimension of the rectangle L1, divided by the distance D. So once we know this value, we stop on the pink line of interest, we move left, and we find the view factor F12. What's interesting about view factors is that we have a few rules that we can use to find view factors in more complicated geometries. One important relation is called the reciprocity relation. So we are considering surface A1 and the surface A2. So reciprocity relation says that the product between A1, so the area of surface 1 times the view factor F12, is equal to A2 times the view factor 2, 1. So we can also define a special case FII, for example, F11. What is that? Is the fractional radiation leaving surface I that strikes itself directly. So for example, if you have a convex surface like this, then F11 is obviously 0 because no fraction of the heat transfer by radiation that leaves surface 1 arrives at surface 1 directly. But in this case of concave surface, then F11, the view factor 1, 1, is different from 0 because some of the heat transfer that leaves surface 1 by emission of radiation then strikes surface 1 itself directly. Another important rule, it's called the summation rule. If you have an enclosure surfaces, the sum of view factors from one of the surfaces of the enclosure, for example, surface I here, of the enclosure to all the surfaces of the enclosure must be unity. So we indicate this by summation, and J runs from 1 to the number of surfaces n. So the summation of Fij must be equal to 1. And of course, this is a consequence of conservation of energy. Another important relationship that we're going to use is the superposition rule. The view factor from surface I to surface J is equal to the sum of the view factors from surface I to the parts of surface J. For example, let's say we want to compute the view factor from surface 1 to surface 3. So here I should have written 1, 3 actually. Let's say we want to compute view factor from surface 1 to surface 3. But this is quite an unusual geometry. We are not going to find tabulated value for this geometry, but we do have tabulated values for cases, for example, such as this one, from surface 1 to surface 2, or from surface 1 to the 2 and 3, so which is essentially the same shape. So we can find the view factor 1 to 2, 3, and we find the view factor from 1 to 2, and all we have to do is substitute it here, and we can find the relationship for F12. All we have to do is subtract F123 F12 from F123, and we obtain F13. The last and also quite useful relationship is called the symmetry rule. Let's take a case, for example, where two or more surfaces have a symmetry about a third surface. Then these two surfaces will have identical view factors from their surface. Let's take a case here, for example. Here there is a geometrical symmetry. If we draw a line, a straight line here in the middle between surface 1 and 2, then the view factor from 1 to 2 must be identical to the view factor from 1 to 3. Thanks a lot, and I'll see you next time.